Good day and welcome to One-on-One Maths Private Tutors. Today we are looking at O-Level and IGCSE Physics for Pure Physics and Combined Science. The topic is elastic deformation. Forces can produce a change in size and shape of an object. This is a characteristic of a force. A force can produce a change in size and shape of an object. The change in size and shape of an object is mostly noticeable in springs. Elastic deformation is change in size of an object due to a tension or compression force where the original shape is retained once the force is removed. So, an elastic band, you can stretch it, and once you remove the stretching force, it will go back to its original shape. When something is deformed, it has changed its shape. So elastic deformation is that change in size of an object due to a force where the original shape is retained once the force is removed. So when you remove the force causing the change or the deformation, the object goes back to its original shape. So this happens in springs. A spring can be stretched and we have a noticeable change in shape at once the applied force is removed. If the applied force is not big enough to permanently deform the spring will go back to its original shape. So that is what we call elastic deformation. The idea of this topic is to look at stretching forces. Forces can produce a change in size or shape of an object. For example, loading a spring will increase its length. An experiment to find how the extension or the increase in length of a spring varies with the force applied is shown below. So what we'll need is a weight holder. This is a weight holder which weighs 100 grams. And these are the 100-gram weights, which are metal discs that will be slotted into the weight holder. We would need one spring with a point and a rule to measure the extension. So we set up the experiment like this, initially without the weights, with our ruler here by the side, making sure the ruler is vertical. The ruler should start from 0 up there, going down. So we take the initial measurement on the pointer of the spring before we load it to the nearest millimeter. Then we add 100-gram mass hanger and measure the new position. So we put our mass hanger there, and the spring should stretch and give a new position for the pointer. Then we read off that. Then we load 100-gram weight. The pointer should move down and a new reading should be taken. Then we load the second weight. The spring should stretch and we get our third reading. We repeat that up to the 6th weight to get our 7th reading. Now for each weight added, starting with the 100-gram weight holder, we should calculate the resulting extension, which is equal to the length of the spring minus original length. So we will have a table of mass, the corresponding weight, and the extension. When we load the weight holder, the mass is 100 grams, which is 0.1 kgs. The weight is mass times gravity, which is 0.1 times 10, which is 1 Newton. So the weight is 1 Newton, and the extension is calculated by this formula. Length of spring, which is the reading on the loaded spring, minus the original length, which is the reading on the unloaded spring. When we add 100-gram weight, the mass now is 200 grams and the weight is 2 newtons. When we add another 100-gram weight, the mass is 300 grams and the weight is 3 newtons. When we add another weight, the mass is now 400 grams and the weight is 4 newtons. So we'll continue for 600 gram weights and then calculate the total weight and the extension that is there. Remember, the extension is the length of the spring when the load is applied less or minus the original length, which is the length of the unloaded spring. Once we have these values there, we then plot a graph of the weight, which is a force in newtons versus the extension in meters. The values we'll get from here when we calculate our extension will be in millimeters. So to get the extension in meters, we divide by 1,000 to convert from millimeters to meters. So we may have our graph in standard units, newtons and meters. So understand the conversion from mass to weight and millimeters to meters. Now the graph of extension against force for a spring is a straight line up to a certain point. From O to P, extension is directly proportional to the applied force. So force is directly proportional to extension because we have a straight line. Beyond P, the extensions are larger for the same increase in force. So point P is called the limit of proportionality, which can be defined as the point on the extension versus force graph where the graph loses its straightness. Beyond that point, the graph becomes a curve. It loses its straightness. That is the limit of proportionality. At a certain point, E, the elastic limit is reached. The elastic limit is a point on the force extension graph where a further load will cause spring to be permanently deformed. This means above the elastic limit, the spring will not return to its original shape once the force is removed. It will be permanently deformed or permanently damaged. The spring will not recoil to its original shape. When this happens, we say the material has undergone plastic deformation. It is no longer elastic. Okay, so when you stretch a plastic, it will not return to its original position once the force is removed. The damage on plastic is permanent. Unlike an elastic, it can go back to its original position. So plastic deformation is when the spring loses its springiness or it is permanently deformed. For elastic deformation, if a material obeys Hooke's law, the extension is directly proportional to the applied force, provided that elastic limit is not exceeded. So if we don't exceed the plastic limit, the extension is directly proportional to the applied force or weight. In this case, we are saying force is directly proportional to extension. So force is equal to some constant K times E, where K is what we call the spring constant. Now, what are the units of spring constant? If F is equal to KE, K is equal to F over E. So the units are, for force we have newtons, and for extension we have meters. So the units are newtons per meter. What force is applied to a spring of spring constant 25 Newton per meter when it extends by 5 centimeters? So we have to look at the units first. We have centimeters and newtons and meters there. We have to convert these 5 centimeters to meters. 5 centimeters is equal to 5 over 100, which is 0.05 meters. F is equal to KE. Force is equal to spring constant times extension. We have our spring constant as 25 newtons per meter times our extension 0.05, which should give us a force of 1.25 newtons. Let's look at this question. Calculate the spring constant for a spring if it extends from an original length of 15 centimeters to a length of 25 centimeters when a load of 5 newtons is applied. So, extension is new length minus original length. Why do we say so? We have a spring that is not loaded. Its length is 15 centimeters. Then when you load it, put a weight on it, its length is now 25 centimeters. So the extension, which is this length, is the 25 minus the 15. So we say 25 minus 15, which is 10 centimeters. But we want this length in meters, which is 10 over 100, which is 0.1 meters. That is our extension. Force is equal to spring constant K times the extension. We want to calculate the spring constant. So we make K the subject of the formula. K is equal to force over extension, which is our force is 5 newtons. Our extension is 0.1 meters, which will give us 50 newtons per meter as our spring constant. Now let's look at related questions. Diagram 1 shows a load hanging on a spring. Diagram 2 shows the load pulled down. So this is diagram 1 and this is diagram 2 with the load pulled down. When the load is pulled down, what happened to the gravitational potential energy of the load and elastic potential or strain energy of the spring? Gravitational potential energy will decrease if we consider this red line to be the ground. Before pulling the spring, as this height, h1, which is greater than this height, h2. Now, gravitational potential energy is equal to mgh, mass times acceleration due to gravity times height. What we have done is to reduce the height where h is the height above ground. By pulling this load down, what we have done is to reduce the gravitational potential energy of the load, since the gravitational potential energy is directly proportional to the height. If the height is reduced, the gravitational potential energy is reduced. So the gravitational potential energy of the load is reduced. Elastic potential energy of the spring. The spring is more stretched here than there. So when you pull the load down, you're increasing the strain energy in there. So the answer is B. Gravitational potential energy decreases, elastic potential energy increases. Let's look at this question. Some students plan to use a spring to make a spring balance with a linear scale. The graph shows how the extension of their spring changes with the load working on it. So extension and load. As the load increases, the extension is increasing. What is the total range of a balance with a linear scale? So the key word here is linear, which means straight line using this spring. So where is it linear? Take our ruler and see where it's losing its linearity. It's at this point where the limit of proportion has been reached. What is the corresponding load? It's 10. So from 0 to 10, it's a straight line. If we want to make a linear scale or a straight line scale, it should be from 0 to 10. So A is our answer. An extension load graph is plotted to show the results of increasing the load on a spring. Which point marks the limit of proportionality? So again, we take our ruler and draw a straight line on our graph. At B, it's losing its linearity. So our limit of proportionality for this spring is B. So that is it for elastic deformation. Thank you.